Okay, so let's get started. Today we're happy to have Mariana from SACLAY. Please go ahead.
Okay, thank you for the invitation. And I'm going to talk about this tadpole problem that we was first paper in collaboration with Josif Bena, Johan Blobak, and Severin Lust came out in October, and then some extensions in October 2000, then some extensions in March, in November, and then I will mention work in progress that should be out very soon, hopefully. So we all know that realistic compactifications should have no massless scalar fields, no moduli, but however, the landscape of Calabi-Yau compactifications is populated mostly from Calabi-Yau, which have lots of moduli. So there was a computation of which Calabi-Yau gives the most number of vacua, and there's this huge number of 10 to the 272,000 vacua from a Calabi-Yau 4 that has this 300,000 complex structure moduli. So these Calabi-Yau vacua with lots of moduli, they appear in the landscape. They're also the corners that can give rise to interesting phenomenology, like the possibility of uplifting anti-de Sitter vacua with small cosmological constant, and the possibility maybe of scale separation as well. So those kind of things require a large number of moduli. Now moduli need to be stabilized, and perturbatively we know how to do that. This can be done with fluxes. But the problem is that fluxes induces charge, and the question is how large is a charge induced by fluxes needed to stabilize a given number of moduli. So the question as it is not very well posed. What does it mean? How large is a charge by the fluxes? But what we mean, well, I'll tell you what we mean, but is so can fluxes that stabilize a large number of moduli have an order 1 induced charge? Can you stabilize a lot of moduli with a very small charge? And the common law says yes, because if you look at equations, if you look at minimizing a potential, it looks like you have equations for all the moduli if you just include very little fluxes, but we argue that this is not true. Furthermore, we believe that there is a relation between the induced charge and the number of moduli stabilized. So our tadpole conjecture says that for a large number of moduli, the charge in the flux, such that all moduli are stabilized at a generic point in moduli space, so we'll see what this means, grows linearly with the number of moduli. And the parameter, the coefficient in this growth is larger than 1/3. And we'll see why this is important. So we argue that there is a linear relation between the charge in the fluxes such that our moduli are stabilized and the number of moduli. So the motivation from this came from black hole microstate bubbling geometries. These have the same mass and charge as the 1d5p black holes, but no horizons. And in the light of ADS CFT, the dual states of this d1d5 CFT. So this CFT counts the black hole entropy, and these bubbling geometries are constructed by having multi-center solutions with 2 cycles between the centers, and there are magnetic fluxes. And the black hole charge is dissolving the fluxes. So we have 2 sort of supporting arguments for the tadpole conjecture. One is some experimental observation that says that the charge contribution from the cycles add up. Otherwise, you get closed time-like curves. So solutions where you have positive and negative charge, adding at the end to a small order 1 total charge, these have closed time-like curves. And also the black hole entropy is a number of ways to put these fluxes on cycles within a given charge. So if it's possible to get this charge with positive and negative individual contributions, then the entropy of the the entropy of the fluxes will be larger than the entropy of the black hole. So this is the motivation, but we are going to apply this to, so our setup is flux compactifications, type 2B flux compactifications on Calabi-Yau manifolds, or F-theory compactifications, as we will see later. So
Mariana?
Yes.
Does this statement require supersymmetry?
Not really. So yeah, I said it's supersymmetry in the case of black holes because we don't know how to do otherwise the counting, but here no, not really. And we'll use supersymmetry and supersymmetry breaking solutions, so no, it doesn't require supersymmetry. Yeah, thank you. So type 2B compactifications on Calabi-Yau manifolds or warp compactifications on Calabi-Yau manifolds, and these have H2,1 complex structure moduli, which are volumes of 3 cycles, and these are typically of the order of 100. And in order to fix these moduli, these are the kinds of moduli that one can fix in type 2B with fluxes, because in type 2B you have 3 on Calabi-Yau, there are 3 form fluxes, and so this fits this complex structure moduli, which are volumes of 3 cycles. So we add 3 form fluxes, which means we add some integers for the integrals over all the cycles of the Ramon-Ramon and the NS-NS flux. And this immediately is not very hard to see that this gives a potential for the complex structure moduli and the dilaton. So if you put this in, if you add this in the action, then the action has a Hodge star. This Hodge star depends. The Hodge star of a 3 form depends on the complex structure moduli, and there's a dilaton dependence, and so you get a potential for the complex structure moduli and the dilaton. The minimum of this potential is when these fluxes are dual to one another, and then this will fix the complex structure moduli. Generically, this fixes the complex structure moduli in terms of these integer numbers m and k. Now, as I said, fluxes induce D3 charge, and the charge in the fluxes is, the D3 charge in the fluxes is given by this wedge product of F and H, so this sum of M and K. So it's easy to see that this D3 charge, so at the minimum, if this condition is satisfied, then this D3 charge overall is positive. So the total sum is positive, but one could think, so these individual terms, they don't necessarily have to be positive. So one could think that one can get order 1 by introducing lots of fluxes here, such that the overall sum is positive. So M's and K's, such that, so +1, -1, and such that the overall sum is positive, but you have lots of contributions to this. And this is what we think. This is what we argue it shouldn't, if you have that, then there are moduli which are unstabilized. So this D3 charge in a compact space, the total charge should be 0. So we have on one side a positive charge, so the fluxes give a total positive charge. If we have D3 branes, they also contribute positive charge. And then negative charge, there are O3 planes, but O3 planes, there aren't too many, in Calabi-Yau in general, there aren't too many symmetries with O3 fixed planes. So there was this systematic study of lots of Calabi-Yau in the Kreuz-Skarke list. And the maximum charge of O3 planes, so the maximum number of O3 planes is of order 100, and the charge is -4, so you get -25 units of negative charge, which is really not a lot. As we will see, solutions require much more than that in positive in fluxes. But fortunately, there are other sources of negative charge, which are the 7 branes and all 7 planes wrapped on curve 4 cycles. Now, the problem once you include these 7 branes is that these have moduli. There are moduli associated to them. There are moduli associated to the D7 branes, and these have to be stabilized by worm volume flux. So this is, having the 7 branes wrapped on cycles is nice because it gives you negative charge, but you run again into extra moduli that have to be stabilized by worm volume flux. And now once you have D7 branes and all 7 planes, and D7 moduli and complex structure moduli is much nicer to work in the language of F-theory, where everything is put together. So the H21 complex structure moduli and the D7 brane moduli are combined in H3,1 complex structure moduli of a Calabi-Yau fourfold. And the two form fluxes that stabilize this H2,1 complex structure moduli and the two form fluxes on the D7 brane, which stabilize D7 moduli, are combined in four form flux on the Calabi-Yau fourfold. And the tadpole cancellation condition now reads, so the charge induced in the fluxes is this G4 with G4. And then I think is that all the negative contributions, so sorry, this is in terms of G4 is given in terms of some integer numbers on the 4 cycles, and this is some intersection matrix. So this is quadratic in the fluxes with some intersection matrix. So again, this intersection matrix is in general not positive definite. So this can have any sign, but at the minimum, the same as OF3 and H3 had to be dual to one another, G4 has to be self-dual. And so at the minimum, it's easy to see that this can be greater than 0. But again, this is a sum of terms, and the terms can have positive and negative, can be positive and negative. And the tadpole cancellation condition says that this has to be less than all the negative 3 charge from D7 and O7 planes, which is very nicely encoded in the Euler number of the Calabi-Yau fourfold. So the tadpole cancellation condition, it's very nice in F theory. And in particular, this Euler number of the Calabi-Yau fourfold, you can write it in terms of the Hodge numbers of the Calabi-Yau fourfold. And so we are interested in H3,1, which are the moduli, the complex structure moduli of the fourfold. These are the moduli that are stabilized by fluxes. So in the limit of a large number of moduli, this chi over 24 goes like 1/4 times the number of moduli. So for large H3,1, which is the limit that we're interested, the negative charge that you are allowed is 1/4 of the number of moduli. While in the tadpole conjecture, we say that the charge induced in the fluxes such that all moduli stabilized grows linearly in the number of moduli, the same as this, but we say that the coefficient is larger than 1/3. So since 1/3 is larger than 1/4, this means that if our tadpole conjecture is true, one cannot stabilize a large number of moduli. Okay, so this is a conjecture. Now let me give you the supporting evidence for the conjecture, but let me pause to see if there are questions. Okay. Okay, so some evidence I will review. So some arguments are from the literature and some we worked out. And there's also work in progress that I will mention. So these are all this Shirabe-Skachu, Tripathi, and Trivedi is type 2b with this number of complex structure moduli stabilized at some highly symmetric point in moduli space where they can do the computation just looking at a few moduli. And we took their numbers for the charge dissolving the fluxes and computed this ratio, and what we get is it's always larger than 1/3, and in particular it's always very close to, it's always 0.40, not always, this is smaller, but all these are very close to the 0.44, which is curious, and we don't have yet an explanation for this. So what I will talk about today is this example of M theory on K3 times K3, and some further work that this was the original example, and some further work that we did on this, and then F theory on a weak Fano base. So F theory in the same limit where they are here, the moduli are the 7 brane moduli. They can be stabilized with 2 form flux, and again you get this ratio of 0.44 of the charge induced by the fluxes divided by the number of moduli. Okay, so let me review this M theory on K3 times K3. This was actually the first example where people discuss moduli stabilization before giving Skachu-Polchinski. This was discussed by Dasgupta, Rajek, and Sethi. And then also work by Aspin Oval Kalos and many other people. So first, let's take one K3. So K3, so we will add four form flags that will have two legs on one K3 and two legs on the other K3. And so we're interested in the second cohomology of K3. And the second cohomology is given by this lattice of signature 319. And fixing moduli means choosing a three-plane of self. So this is this has mixed signature, and fixing moduli means defining a holomorphic two form and a symplectic form on this on this 22-dimensional space. And this is equivalent as choosing a three-plane sigma of self-dual two forms, because these have to be self-dual. And so this geometric way of seeing how moduli are fixed then is very nice, because it translates into some algebraic problem to see when flux is fixed, this moduli. And the point here is that we will require smooth compactification, so no orbifold singularity, because if they are orbifold singularity, they are non-abelian gauge groups, and these typically have large ranks, and also in particular they come with massless moduli themselves. They come with massless matter that you need to fix with extra fluxes. So we think at the end of the day this is a lose-lose situation. So we require no orbifold singularity, and there's an orbifold singularity if there's a root, so an element of norm 2 in this lattice, such that is orthogonal to this 3 sigma plane. So now, so fixing moduli in K3 times K3 is done by 4-form flags, and the 4-form flags we choose to have. So there's also 4-form flags that have 4 legs on one K3 and 4 legs on the other K3. That 4-form flags can fix the relative volumes of the K3s, but we're not that place along for the ride by itself. So that's an easy flags. So we didn't look at that. It's not particularly interesting. But we looked at these 4-form flags that has 2 legs on one K3 and 2 legs on the other K3. So this can be written in terms of some 22 by 22 integer matrix. And these are the basis of 2 forms on K3. So this gives a potential to fix all K3 moduli, so not just complex structure, but also scalar moduli here in this particular case. So this is not really a Calabi-Yau fourfold, it has a SU2 holonomy. Sorry, that would be SU2 times SU2. So here you can, so here you, or the solution in general, a background on this Calabi-Yau will have an equal 4 supersymmetry, and so the fluxes have potential to fix all K3 moduli, except the volumes, but the relative volumes you can fix with 4-form flux on one K3 or on the other K3. And the nice thing about the K3s is that this moduli stabilization can be turned into an algebraic problem, which was studied by these people, by defining a map that goes from H2 of K3 to H2 of K3, which is quadratic in the fluxes, and then it has these intersection numbers here of one K3 and the other K3. So this map, this map is the map that appears in this quadratic form, is a quadratic form that appears in the potential, and it's not very hard to see that all moduli are stabilized at regular points if this quadratic map is diagonalizable with non-negative eigenvalues. And there are three eigenvalues that correspond, whose eigenvectors have positive norm, and there are 19 eigenvalues whose eigenvectors have negative norm. So if this map is diagonalizable in this way, where all these are non-negative, and all A are different from B, then the moduli are stabilized, because if there's an A that is equal to a B, then one can make a combination of those A and B to rotate, because these A's are the ones that define what is the three-plane sigma. So if an A is an equal, if an eigenvalue here is equal to this, I can rotate it a little bit and still keep it positive norm. So that means I can rotate the 3 planes. So there are unstabilized moduli. And then we also require, in order to have no orbifold singularities, that there are no roots in the lattice orthogonal to sigma. So the goal is to find matrices satisfying all 3 requirements and minimizing the flux charge. So this would be very nice. So the flux charge is just the trace. This is just a trace of this matrix. So it will be very nice, and we're still hoping that maybe this problem has some solution, has analytic solution in using number theory, but so far we didn't find that. So what we did here is to use an evolutionary algorithm to find the best fitted end. So this evolutionary algorithm, our optimization algorithm, is inspired by biological evolution. So there's some population, some mutation between the population, and some selection. And we start with a random initial population. So a bunch of matrices, which are integer, 22 by 22, or vectors in R484. So this is very large to work with. And then for each matrix, you mutate some entries using other elements of the population. And then from the original unmutated, you select the one that minimizes a fitness function. So we construct a fitness function that gives a penalty if any of these is not satisfied. So we needed the matrix to be diagonalizable with all different eigenvalues and no root orthogonal to sigma. So there's a penalty, and there's a penalty for a large flux charge. And there's some weights, and we play with the weights such that the solution converges to solutions that satisfy this and have a small flux charge. So this condition, that having no root orthogonal to sigma, is an NP-hard problem, and this took us very long time to implement. And then also we perform some local search around the minimum. So the minimum of this, we also perform some root form local search to minimize that even further. So what we found is lots of matrices that have Q flux equals 25, but no matrix with less Q flux equals 24 or less. And in particular, 24 is very interesting because it's a number is precisely chi over 24 for K3 times K3 is precisely 24. So in the K3 times K3 case, which is not very large number of moduli, already one cannot stabilize moduli at a generic point within the tadpole. And if we look at this tadpole conjecture constant, which is the charge inducing the flux is such that all moduli are stabilized divided by the number of moduli, what we get is this 0.44, so larger than 1/3. So our tadpole conjecture is satisfied here. Now, since these are very large matrices, we wanted to make sure, and we started playing by looking at smaller dimensional lattices, so sort of toy models, because there are no Calabi-Yau twofolds so with these lattices, but everything. But just to make sure that indeed there's always a minimum flux inducing the charges, and in order to have a solution with all moduli stabilized at some generic point. And indeed, there's always a minimum charge. And here the minimum charge is related to the dimension of the lattice in some more or less in some linear way. But in particular, yeah, so these are examples that converge very, very fast. So here you can see very clearly that that it's not a problem of not having enough statistics to show that there is always a minimum charge. Okay, and something that we're looking at now is analytic supporting evidence on K3 times K3. We looked at this Aspinwall-Kalosh paper where they look at M-theory fluxes leading to attractive K3 surfaces. So attractive K3 surfaces are such that this Picard lattice, which is, so in this 22-dimensional lattice, most of the forms are 1-1 forms. So the rank of this H11 intersection H2 is maximum is 20. And so the other two will generate the omega the 2,0 form. And they add 4-form flux of this form. And this gamma has to satisfy. So for example, the real part of gamma has to be integer for this to be a solution. And there's also other conditions with the real part of gamma and the complex structure in omega 1 and omega 2. But they show that this gives always this type of flux, fixes moduli, fixes the complex structure moduli of each K3, giving an attractive K3 surface times an attractive K3 surface. And Brown, Kimura, and Watari have listed all solutions with flux within the tadpole bound. And what we did is using some Nishimaya method, some way to look at the F. So we looked at the F theory uplift, which is defining, so we need to find an elliptic vibration and then see what happens with all the solutions. So we could scan all the solutions with flux charge up to 26 and see what are the gauge groups. And what we see, and we're doing this up to flux 30, what we see is that indeed they all have non-abelian gauge groups, and they all have non-abelian gauge groups of rank of large rank, rank 6 at most. So one question is, what is the minimum flux to have non-abelian gauge group? And very likely 30, but we still have to play with this. But again, so in order to have non-abelian gauge group, or in other ways, stabilize moduli at a generic point in moduli space, then we need a large charge inducing the fluxes. And we need, in the case of K3 times K3, larger than what is allowed by the tadpole. Okay, now more supporting evidence, which is again some work to appear, is at the asymptotic limits in complex structure moduli space. So we look at a certain number of moduli n, and we see what happens if they are stabilized in a region where the sections, so we divide it into actions and sections, and the sections are much larger than 1. And there's a whole machinery of asymptotic Hodge theory, where you can write explicitly the action of the Hodge star in terms of the actions and sections. And again, remember, so the Hodge star is important here because the solution G4 has to be self-dual, so equal to star G4. So here one can run the moduli stabilization in this limit. One can run the moduli stabilization for this n moduli very explicitly. One can have explicit equation for the moduli in terms of the fluxes. And what we see very clearly is that one flux, or let's say one contribution to the charge induced by the fluxes, corresponds to one modulus fixed. So if you want to fix n moduli, then you need to have a flux induced which goes linearly with the number of moduli. Here is very easy to see, but I don't want to show it because you will need to get into this. I will need to get into the details of this asymptotic Hodge theory, which I don't want to. But once you know that, then this is very straightforward to show. So yes, straightforward to show that the tadpole grows linearly with the number of moduli. So more. Yeah, I don't know. Let me go back and once again to see. Oh, there was this G4 star G4 missing here. Yeah, that's why so you need the action of the Hodge star, and here is written explicitly, and you see the moduli stabilization very explicitly. But so let me pause to see if there are questions.
So, Mariana, what is perhaps you said that this problem presents itself, is supposed to present itself at large number of moduli, right? How large? At least 24, is that the idea? I mean,
yeah, it's a good question. We don't know. I mean, for the K3 times K3, which has here all moduli stabilized, is order of 50 moduli, we see already the problem. But yeah,
the conjecture is that eventually you have this behavior.
That eventually you have this behavior, yeah.
Okay.
Yeah, and we cannot really study examples with a large number of moduli. So far, other than this K3 times K3, or in this limit of large complex structure moduli, where here we can do n moduli.
But they say in any case this is important because you need a large number of moduli later on if you want to use it for KKLT or whatever. I mean,
exactly.
To achieve a small cosmological constant.
To achieve a small cosmological constant, yes. Scale separation, that's a little bit less straightforward, but yeah.
Okay, but so the spirit is that you're presenting evidence that for large, that eventually this behavior sets in.
Yeah.
Okay.
Is there a hint from this analytic analysis how you might prove this statement?
Yeah, good question. I mean, here, yeah, good question. So here you see the tadpole as a sum of, so in this limit, so there is this SL2 orbits, SL2 representations of the monodromy matrices around this moduli going to infinity. And what you see is that that you need a flux in each of these SL2 representations to fix so one flux in SL2 representation fixes one modulus. So you get a sum of fluxes in order to get n moduli fixed, you get a sum of fluxes in n of these SL2 representations. But yeah, I don't. I don't see how to carry that because it uses heavily this SL2 orbits, SL2 asymptotic Hodge theory, which you don't really have in the bulk of moduli space. So unfortunately, I don't see how you can use that.
Do you have a sense where the third is coming from, even in this case?
No, I should be honest. We should have put a 1/4. It's just that all the examples where the 1/3 is basically what is, was some rational number larger than 1/4 and fitting all the data. But it's not that, it's not that we are tied to the 1/3. So we should have probably put, this was a fight in our collaboration, whether to put 1/4 and which is the extreme value or to put something. And all the examples seem to have, all the examples seem to have it larger than 1/3, but no, there is no rationale for this 1/3.
Thank you.
Other questions?
I have a funny question. So if the conjecture holds an at large in a generic point, well, even in any case, fluxes are discrete. So a generic point in moduli space is not going to be a point that's stabilized, right? I'm not missing something here. So stabilization is going to pick some discrete subset of moduli points. And what you're saying, I think in the K3 example, I understand, is all of these will have maybe enhanced gauge symmetry. Is that a way to say this? Conclusion?
Yeah. This is, yeah.
So is what you're saying that if we want to run KKLT-like scenarios, we have to look at it turns out that the special points that moduli stabilization picks are special in some other sense. Maybe they all have enhanced gauge symmetry.
Yes, yes.
Okay, I understand.
Any other question before I get into the D7?
Actually, maybe this is not the right time to ask. Meant to ask you at the end, but since we interrupted already a few times now, so there were other papers claiming that they could. So there was a paper by McAllister and collaborators where they claimed to have a very small cosmological constant, and then there was a paper.
Very small superpotential, you mean?
Sorry, yeah, very small value. But don't they also say the cosmological small cosmological constant in string theory? And that was maybe it was that I thought it was with KKLT. So this seemed to indicate that they had somehow.
Yeah. So in the examples they work out, you put yourself at a very special point, very symmetric point in moduli space, and then they look at stabilization of a few moduli. But yeah. So because that's a if you don't, it's impossible to do this game with really many moduli. So they look at points that have a large some set 7 symmetry, I think it was, or something like that, and they only look at the
moduli that are kept by this by this symmetry, that preserve the symmetry. So one doesn't know what happens to the others. Okay. And then maybe asked this already, but at some point in some other occasion, but there was a famously also a paper by Marquesano. What's the story there?
Yeah, so the story there is that so they have they also turn this moduli stabilization into some algebraic equations, which are implicit, and it's not clear that this has a solution. And actually, what we are realizing here, and they have they stabilize lots of. According to these equations, you can stabilize lots of moduli with fluxes that don't enter in the tadpole. Those will correspond to, so here in this asymptotic Hodge theory, you can divide the moduli into the SL2 representations into heavy, light, and the rest, which are neither heavy or light, which is basically how in this Hodge star, basically whether you have positive powers of the S moduli, negative powers, or something indefinite. And they use this, what they use is this V-rest, the moduli which are the moduli which are the SL2 representations, which are neither heavy nor light, in order to stabilize moduli. And what we see in this paper is that actually in Calabi-Yau, that space is empty. There are really no states. There are no really no vectors in that in those SL2 spaces. So I think eventually their equations they don't have a. One should see somehow that they don't have solutions, because they're using a trick with a space that doesn't really exist. But it's hard to see, because they give some implicit equations, and one has to work out in examples what happens and what and whether how the tadpole charge grows.
It's hard to see from their paper. This is what you mean.
Yeah. No, I know. Yeah.
Okay.
We try to also solve them. I mean, Severin tried to solve it, and it could work for grand total of 2 moduli. But and also, if you look intuitively, if you look at what they're claiming, is essentially I mean, if you just look at the flux configuration they are claiming, intuitively it looks completely bonkers. But that's another.
Yeah, so they have again they have lots of fluxes that don't contribute to the moduli to the tadpole, and those are the fluxes in these SL2 representations, which we show that they are empty. So yeah, I think that thing doesn't work, but it's in a non-trivial way. It's not.
I see. It's a pity that they are not here to defend themselves, but okay, and that's for another time. Thank you.
Okay. So now this more analytic supporting evidence, which is the 7 moduli stabilization. So we're looking at F theory, but in the same limit. So F theory on a Calabi-Yau 4-fold fiber over a base in the same limit. And the number of 7 moduli is directly written in terms of C1 of the base. And these are stabilized by two-form flux, which means, so if you have a D7 brane, so this can move. But once you turn on flux, there is some, so the flux is dual to some, the two-form flux is dual to some curve. And then this, now if you move the brane, then this curve will not be holomorphic anymore. So this, now the D7 is fixed at this point. So that's geometrically how you see this moduli stabilization. So this D7 moduli stabilization in terms of the two-form flux. And the tadpole, so this two-form flux has a charge induced. The charge induced is given by this. And this has to be less than the negative charge coming from the 7 and O7 planes, which in the sense of this chi over 24, it can be written, so in the same limit, it can be written again in terms of C1 of the base. So in terms of the same number that appears here in the number of moduli. And if you do the ratio of the charge divided by the number of moduli, you get very close to 1/4. So it's not exactly the 1/4 of F theory. So this allows for a little bit more of charge inducing the fluxes. So the tadpole has this ratio of charge, negative charge divided by the number of moduli to be a little bit larger than the F theory counterpart. And our tadpole conjecture, which is a conjecture for type 2B and complex structure moduli and type 2B and the 7 branes, or all together in F theory. But so the version for the 7 branes says that this charge induced in the flux is such that all the 7 moduli are stabilized is larger than 1/3 than the times the number of moduli. And again, since 1/3 is larger than this 1/4, if it's true, one cannot stabilize a large number of the 7 moduli. And here we verify this for any weak Fano base. So this is a huge number of manifolds of the order of 10 to the 15. And the tadpole conjecture is satisfied up to a subtlety that I will tell you. So the way to verify this is, again, so the moduli the flux is dual to some complex curve, and one can write the number of moduli in terms of something that looks like a degree. So in the case of toric varieties, so this is the intersection of the curve with the anti-canonical bundle, and in the case of toric variety, this will really be the degree. And this has to be, so the number of moduli is given in terms of C1 on the base. So if we want the number of stabilized moduli to be the number of moduli, then this is equal to this. And then what we show is that the charge induced in the fluxes is also given by the same degree. And then this contribution from the genus, this extra negative contribution. So for large number of moduli and fixed genus, so if we take a fixed model genus, then we recover that is the number of the charge induced in the fluxes divided by the number of moduli is again this magic 0.44. So you cannot stabilize all the 7 moduli by tadpole cancellation condition. and the tadpole conjecture is satisfied. So this was a huge generalization from some paper by Colinucci, Denef, and Esole, where they studied this result for a particular base, CP3 base, and for genus 0. So we first extended for all toric geometry, but that was a bit straightforward, and then in general for any weak Fano base, and we get the 0.44. Okay, so in the last minutes, still have 15 minutes. Let me just show this. So we talked about why large. I mentioned that the large number of moduli is needed for the sitter, but let me show you why. So we show so KKLT has this throat with an S3 at the top. This is the S3 is rated by Ramon fluxes, and there are NSNS fluxes that go into the bulk Calabi-Yau. And there are anti-D3 brains in the bottom, and then RAP-D7 brain, but we don't care about it. And the first step in KKLT is to fix this complex structure modulus, which is the size of the S3 with fluxes, with this K and M. You fix it at some value. Now what we looked at is the potential. So you can get this from a potential. You can get a potential in terms of this conifold modulus. But what we looked at is the warped effect. So we looked at the warped effective field theory, which was studied of this conifold modulus, which is a bit ugly and studied by Douglas and Torroba. And we saw that it has a very different behavior for small s. So it has the same minimum as the unwarped. So this will be the unwarped potential, and this is the warped potential. They have the same minimum, but they have a very different behavior here, which means that now once you add the anti-D3 brain, then this wants to collapse the S3 unless there is a large charge. So you need a very large charge in the fluxes. So you need G string M to be larger than this 6.7 to avoid the S3 collapsing to a singular solution. So and there was a similar bound obtained by Joseph and collaborator for demanding the existence of a Klebanov-Strassler black hole. So this means you need to have a large large Ramon fluxes, and on top of that you also need large NSNS fluxes, because if you look at the hierarchy, the hierarchy, which is in order to get a small cosmological constant or a large hierarchy, you need this throat to be long, and this is given by this combination of K and G string M. So, and if you multiply and divide by M, what you get here is the G string, the square root of G string M that we found before. So this is larger than, so this should be larger, but here is our minimum. And this K and M is the flux induced, the charge induced by the fluxes in the throat. So just from these fluxes. And in the bulk of Calabi-Yau, there will be more fluxes, but so this is larger than this. So if we want this to be at least 2 orders of magnitude, which is a minimum requirement, you need this charge in the fluxes to be of order of 100. And this means that you need to have a large number of moduli. So already you cannot do it with orientifold planes, which we said at most give you 25 units of charge. So you need a theory, or you need the D7 brains wrapped on cycles, and you need a large tadpole charge. So for this order, I think you're already in the limit of large number of moduli. And then this large number of moduli need to be stabilized with extra fluxes, and then we run, this cannot be done if the tadpole conjecture is true. So if our tadpole conjecture is true, there is no anti-brain uplift and no de Sitter vacuum a la KKLT. Okay, to conclude, no, it's early. we can have more discussion. So the tadpole conjecture says for a large number of moduli n, the charge induced in the flux is such that all moduli are stabilized. Again, at the generic point in moduli space grows linearly with the number of moduli, and the coefficient is larger than 1/3. So this conjecture is supported by several examples. So previous constructions in the literature that we looked at, and then this evolutionary algorithm for K3 times K3. Then we did this kind of flux solutions, particular flux solutions, so not leading to, not any K3, but these attractive K3s that have only one complex structure moduli. So this is easier to analyze. But so what we saw here is that any solution, so here we could do an analytic search of all solutions, and any solution satisfying the tadpole cancellation condition, so whose charge is less than 24, less or equal than 24, they have non-abelian gauge groups. So moduli are stabilized, but not at the generic point in moduli space. And there is an analytic computation in the asymptotic limits in moduli space, which says that the charge inducing the flux grows linearly with the number of moduli. And an analytic computation for T7 moduli. So if this is true, one cannot stabilize a large number of moduli in F theory or in type 2B limit. So these 10 to the 272,000 vacuum are not phenomenologically relevant. If true, there is no anti-brane uplift in long warp throws, no de Sitter vacuum like KKLT. And then one is forced to work with Calabi-Yau manifolds with few moduli or other geometries, but other geometries the moduli in other geometries are probably have the same problem, and they are measured with other cohomologies, maybe the Rho cohomologies or something else, but they have to be stabilized, and one probably runs into the same problem. Okay, so thank you for listening, and more questions, discussion this time.
Okay, let's thank Mariana, and then we could take a couple of questions. You can freely unmute yourself if you have a question.
May I ask a question, please?
Go ahead.
Thank you. Thank you for the talk. Is this a small question regarding, you were taking this F3 uplift in the case of attractive K3 cross attractive K3, and for that you required an elliptic vibration.
Mm-hmm.
There's more than one elliptic vibration that attractive K3s have. So your answer doesn't depend on the specific elliptic vibration that you choose?
So no, so what we look is, so we take one of the K3s and we look whether this has an elliptic vibration, and then if it has an elliptic vibration such that there are no non-abelian gauge groups, so that there are no roots in the lattice of the base. So we look at all possible elliptic vibrations of so we choose one of the K3s, but yeah, one can study one or the other, and indeed one might have one elliptic vibration where there are no roots, but yeah, what we see is what for all possible elliptic vibration, whether there is for all possible elliptic vibration, whether there are no roots for any elliptic vibration, where it doesn't allow any elliptic vibration with no roots.
Thank you. So you checked all elliptic vibrations with this particular condition of no roots.
Yeah. Yes.
And one more question. So attractive K3 is given as, it's a theorem that it's given as a Kummer K3 surface associated with the product of two CM type elliptic curves.
Yes.
And the complex multiplication. So I'm wondering complex multiplication by an imaginary quadratic field. So in the case where you have these two attractive K3 surfaces, the CM fields that show up on both sides have to be the same, or they can be different?
No, they can be different. They can be different. There's some condition, there's some yeah, compatibility condition that they have to satisfy. That the determinants, the product of the determinants is a perfect square in order for it to work, but they can be different. Yeah.
I see with this condition. Thanks. Can you, I mean, there are other questions, so maybe but I just wondering if there's a quick explanation for this arithmetic condition, that the product of the determinants is a perfect square.
Yeah, no, I don't think it's I mean, it's not very hard to see, but yeah, I don't have some.
It just comes out of computations.
Yeah, it comes out from the computations. Yeah.
Thank you.
You're welcome.
So, may I ask a very simple question?
Yes.
So, I mean, so if your conjecture is exactly true, I still don't see why you have this strong pheno implications, that basically there's no KKLT, no landscape, and so on, because you don't need to be in principle, I don't see the need to be at a generic point modular space, right? I mean, it's conceivable that you have to live with a large gauge group.
Yeah, if you know how to lift the moduli of those large gauge groups.
But they're automatically lifted once you break SUSY. So if supersymmetry is broken, I mean, you're talking about superpartners of the genus, basically, right? I mean, the adjoint fields which are always there.
Yeah.
I don't think they are generically massless. I mean, once you break supersymmetry, you can calculate there will be soft terms. So it's interesting to study whether those are maybe unstable or some other problem, but it's not obvious, I think.
Yeah. So yeah, this will be stabilized with other mechanisms which are which can have their own problems. But indeed, so yeah, maybe one should say the Sitter-Bakula KKLT will have a large a priori, as it is a large number, a gauge group, a large gauge group. Yeah.
Which is very interesting, I think. I mean, it's an interesting consequence. If anything of this is true, I mean, it seems to be not necessarily deadly, just maybe a surprising, interesting consequence.
Yeah. One can turn it into a more positive, yeah.
It's very hard to see how you can stabilize because you have over the n squared moduli. So you might need the theory on these D7s to confine or something. But then if you have, for example, some D7s which have like a super mega big number of moduli which are not stabilized, then maybe you get some confinement and you can stabilize this all these fields. But it's very hard. I mean, the physics is going to be very different from the KKLT one. I mean, you'll have extra fields, you'll have extra fluxes, because once you confine, let's say you have a singularity, you have Klebanov-Strasser, and then you have some singularity in the middle of the Calabi-Yau, which is hunky-dory, and if you put stuff there, it will confine. You can stabilize some moduli, but you have to pay a price. You have to pay a price either with 1,2 fluxes or with something else. I don't think this will come for free. So
no, if you don't do that anything. So naively you have a large n equals to 1 or n equals to 2 maybe gauge theory, but supersymmetry in the total space is broken. I think you can be certain that all scalars get a mass. I mean, if
absolutely the theory will confine, but once the theory confines,
no, I'm not talking about confinement. It's not about confinement. It's about simply supersymmetry breaking. So these models all have supersymmetry breaking at the end, and scalars get a mass. If it wasn't like that, we would be able to solve the hierarchy problem. That's a generic prediction that scalars get a mass.
But the scalars get a mass again. But the point is, there's also confinement in this theory. It's an n equals 1 theory, which has a bunch of scalars.
That's a further thing. Confinement is an extra interesting possibility, yes. But even before confinement, you're not expecting massless scalars.
But by the way, you don't give mass to scalars by putting branes in fluxes. You give mass to scalars. So, for example, if you look at the 3 branes and you put them in some 1,2 fluxes, there's no Lagrangian term on the D3 brane in the D3 brane war volume action. There's no Lagrangian term which gives mass to the scalars. If you look at the D3 brane, I mean, we can talk. We can discuss later.
Yes, maybe let's take a few more questions, and then after we do the recording, then we can have this discussion. I think it's very interesting, but maybe we should give opportunity to other people to ask a few more questions. Please ask a question if you have. Okay, let's thank the speaker one more time, and then we can turn off the recording, and then